How do you do? Here, let me adjust the camera here a little bit. There we go. That's better. Whoops. Okay. So my name is David Jeffrey. I am Dual Science Solutions, and I have made this model lesson in chemistry so you could have some sense of what type of teacher I am and my presentation style, and other aspects of teaching. And so I hope you enjoy this. It's meant to be a model, but it's also meant to be instructive. If you struggle with an understanding of the atom, you're not alone. There's some very strange concepts that are contrary to our everyday experiences, which makes this particularly difficult, but also makes it very fascinating. All right, so welcome again, and let's get started. Okay, well, what is this? It's a lot of history. So why are we looking at history in a chemistry presentation or lecture? It's because it's been my experience that that jumping right into a new topic, especially one as unusual and peculiar as the nature of the modern atom, is very difficult without at least presenting some of the history and the development of some of these concepts. They didn't come from nowhere. They came from men and women who lived real lives and who had many failures before they had the tremendous successes that they had through a lot of hard work. And it was an incremental improvement in understanding over a long period of time. And I really think it's helpful to at least see this. So actually, we go all the way back to ancient Greece in the 5th century BC, where ancient Greek philosophers believed that matter was made up of tiny, indivisible particles. They can't be cut. They're the simplest components of matter. They call these atoms, which means uncuttable in ancient Greek, apparently. Now, they had no evidence for this, which is interesting. They couldn't prove this in the 5th century BC. They didn't have any instruments that would demonstrate this. They couldn't do the right experiments. Even if they could imagine the right experiments, they just thought this must be so, which is very interesting. And of course, they were mostly correct. Now, they're not correct about atoms being uncuttable. More about that later. Then we jump all the way to the early 1800s. See if I can get a cursor here. No, I can't. We jump all the way to the early 1800s. John Dalton, English physicist, chemist, develops his model of the atom and his law of multiple proportions. This is the first evidence that is cited that that matter is comprised of tiny particles called atoms. In 1897, another English physicist discovers the electron, the first of 3 subatomic particles, right? Subatomic, meaning smaller than the atom, contained within the atom. And right there you can see that atoms are certainly divisible. They are cuttable. Otherwise, they couldn't be comprised of subatomic particles. In 1909, Thomson's student, Ernest Rutherford, basically discovers the proton by designing a brilliant experiment called the gold foil experiment. And by the way, when I teach and tutor in chemistry, I feel it's very important to go through the classical experiments. They teach so much. These are the great experiments of science and of chemistry, and they really do teach so much. And it also helps the student understand and appreciate that chemistry is very much an experimental science. Another English physicist in 1913, or chemist, these are basically physical chemists. It's physics plus chemistry, discovers isotopes. We'll say more about isotopes. Then I have two of these entries bolded because they're so important to our understanding of the modern atom. And the first of these was accomplished by a Danish physicist named Niels Bohr, who developed the Bohr model. And this is the first time that scientists propose that atoms are quantized systems. We'll say much more about that shortly. Quantized systems. So just remember that. This was a revolution, an absolute revolution. In 1916, an American chemist, Gilbert Lewis, uses these principles to describe the nature of the chemical bond as involving the electrons or the outer electrons. We call those the valence electrons of atoms. And then in a 3-year period in the mid-1920s, primarily in Germany, there are tremendous leaps forward. The de Broglie wave equation and the concept of matter waves and electron waves, Heisenberg's brilliant uncertainty principle, and Schrodinger's wave mechanics equation take us so far into the modern age. In 1932, the third subatomic particle, the neutron, is discovered by James Chadwick. Okay, what is this? It's a building. It's a very famous building, because if you go through these names, English, 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 a lot of this science, of these developments, of these discoveries were discovered not only in the same country, but in the same building at the same university. This is the famous Cavendish Labs at the University of Cambridge. And these are just some of the names. You may recognize some of them. That's Watson and Crick, right? Nobel Prize for the elucidation of the double helical structure of DNA. There's James Chadwick, right? Discovery of the neutron. Ernest Rutherford, discovery of the proton, right? And there's a longer list than this. It's remarkable and very interesting that at certain times in certain places, right, the combination of personalities is just right and the environment is just so, right, that particular location, right, puts out discovery after discovery after discovery, sort of center of excellence. It's interesting that how science works. This is a common recurring theme in science. Okay. Now, if you remember, Dalton was the first time, James Dalton, his theory was the first time really that scientists cited evidence for the atom. And this was about 1808. We don't know exactly for sure. It's about 1808, early 19th century. And Dalton's atomic theory were 5 statements. These 5 statements. Okay? Let's go through these. Elements are made of extremely small particles called atoms. Okay? Atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements combine in simple whole number ratios to form chemical compounds, and in chemical reactions, atoms are combined, separated, or rearranged. Now, I wonder if you know, that's why we have the question marks, I wonder if you know which of these statements turns out to be correct and which turn out to be incorrect. Take a moment, reread these statements, okay, and I will tell you right now that 2 of these statements are not correct. Okay, now, for 1808, getting 3 out of 5 is pretty good, right? 3 out of 5 very important aspects of the nature of the atom is really, really good. But 2 of these are not correct. Can you identify the 2 that are not correct? Yeah, it's these 2 right here, right? Now this one here, atoms cannot be subdivided. Well, we know they can be subdivided. That's why they contain subatomic particles, right? And they can be split and broken, and they can be destroyed, right? That's what we do when we run a nuclear reactor to generate electric power. Right? So atoms can certainly, under special conditions, certain atoms, not all atoms, can be split, can be destroyed, and can also be created. That's fusion. This is fission. That's fusion. It's the energy of the sun, right? What about this one? Atoms of a given element are identical in size, mass, and other properties. No, there are, let's go back. Right over here, the discovery of isotopes. And isotopes are atoms of the same element that have different masses because they have different neutron counts. So Dalton did pretty well, but he did not appreciate that isotopes are a thing. Okay. Now, let's go on with our introduction to what will eventually be our understanding of the modern atom, its nature, its properties, its behavior. And of course, all of this is leading up to what? Chemical bonding. You can't understand chemical bonding without understanding the nature of the atom. And you can't understand chemical reactions without understanding chemical bonding. So that is the logic here. Now, take a look at these two depictions of an atom. On the left, you see something that is very familiar. You see this symbol all over the world. Any sort of radiation research at a university will have this symbol on the door as a warning that there's radiation in use in that particular laboratory, right? Or certainly, nuclear reactors have this symbol all over the place. This is the international symbol. Now, this is my depiction. It's not very pretty, but this is the basic idea. Sometimes there's just a circle in here for the nucleus. This is the basic idea behind the representation of an atom. But I say no, this is not correct. It may be in use all over the world, but it's not correct. What's much more correct, maybe not yes, but what's much more correct is a fuzzier picture where we don't have, right, the red are electrons, the blue are protons, the gray are neutrons. The protons and neutrons are contained in that small dense nucleus. That was Rutherford's discovery, the gold foil experiment. And the electrons here are nice and well defined on these nice little orbits or paths. Well, that is not what an atom looks like or acts like, right? An atom acts more like this depiction where the electrons are somewhere in this dark red region or somewhere in this brown region or somewhere in this pink region. But we don't have little red balls that we can that are basically orbiting the nucleus. Get rid of that idea. Electrons do not orbit the nucleus the way the moon orbits the Earth. They are contained within these energy bands. But in fact, we never know exactly where they are. We never know exactly where they are, and we never know exactly where they're going. I told you this gets weird, right? Okay. Before we get into that weirdness, this is something that's less weird. It's just simply a list of the 3 subatomic particles, the symbols that we use to designate them, their mass number, their exact mass in units of AMUs, more on that later, their exact mass in units of grams, you know what grams are, right? Their relative electric charge and their absolute electric charge in coulombs. Now, the neutron is electrically neutral, so it has no charge. And the electron is said to have a mass number of 0. Of course, it doesn't have 0 mass, otherwise it couldn't be a matter particle, right? But it has such a small mass compared to the proton and the neutron that we say that essentially electrons are massless. All right? Okay. So like I said, we'll come back to AMUs later. We'll come back to isotopes. We won't forget those things, but I want to go on. I want to go on because I want to show you the most important aspect of the revolution in physics and our understanding of the modern atom, which occurred in the early 20th century. This is the quantum theory. Now get ready, because this is very strange, but it's been proven over and over and over again. All right? So the Heisenberg uncertainty principle can be stated in this mathematical fashion. And basically this is saying that the change or variability in the position of an electron, this is for electrons and atoms, times the change or variability in the momentum of that electron is at least as great, right? Inequality, at least as great as h, which is Planck's constant, which is a number, divided by 4 pi. So this is some number here. Now Planck's constant is very, 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 very small, right? And so this is a very, very small number, but it's not 0. It's not 0. This little equation has tremendous, tremendous consequences, okay? Because what you're saying here is that the smaller the variability or uncertainty in the position, the greater the uncertainty or variability in the momentum, right? Or the less the variability or uncertainty in the momentum, right? The greater the uncertainty in the position. And remember, momentum of a body in motion is its mass times its velocity. That's its path. Velocity has direction. So what we're saying here, this is amazing. What we're saying here is that if you really want to know the position of an electron in an atom really precisely, you can do that. You can find it. Okay? But you're going to give up knowing where it's going to be in the future. You're going to give up its future path. If you really want to know its future path, you can do that, but you're going to give up where it is right now. How weird is that? Okay? This is the idea that by looking for something, you affect the behavior of that thing. And there is a physical basis for this that maybe we'll discuss some other time. Okay? And this is not the world we live in, right? We know that when we get in our automobile, okay, we know we're starting in a certain position, we know we go a certain direction, and there's no uncertainty in this, right? Unless we get lost, right? Unless we get lost, and then we look at a map or use our GPS system. Okay, but there's this concept of not knowing exactly where something is and where something's going to be, given the basic laws of physics, Newton's laws, is completely alien to us. This is not the world we live in, but this is the world of the electron. And it's a different world. Okay. All right. Now, continuing with these weird ideas, we get to the Bohr model. Niels Bohr, tremendous Danish physicist and a good friend of Albert Einstein's. Remember we said that atoms really don't look like this. They look a lot more like this, and it really has to do with the nature of the electron. Because look, the nucleus is the same in both these models. It's basically a bunch of protons and neutrons that are packed together. That hasn't changed. It's the depiction of the electrons that has changed so much. And Bohr said that electrons in atoms, and he was referring to the hydrogen atom. So the hydrogen atom is, of course, the simplest atom. Hydrogen is the simplest element. I think you know this. Its atomic number, its element number 1. It has 1 proton and 1 electron. Okay? And it has 1 neutron or no neutrons or 2 neutrons. Those are isotopes. Later on that. But Bohr said that electrons in atoms in general can only exist at certain energy levels. So in other words, if electrons are within this region or space of the atom, this is a cross-section of an atom, right? They have energy level 1. They all have energy level 1. If they're in this space, they have energy level 2. If they're in this space, they have energy level 3. But understand something. As you go from energy level 1 to 2 to 3, it's not smooth. Suppose energy level 1 is has a value of 3, whatever the units are, right? You go from a value of 3, energy level 3, to a value of perhaps energy level 7, to a value of perhaps energy level 21. You go from 3 to 7 to 21 with nothing in between. No other energy states are possible. This is like you get in your car and you start your car up, and or perhaps you're at a traffic light and the light is red, so your car is stopped. But then the light turns green. You put your foot on the gas, right? And what does your car do? Well, it goes from 0 to 0.1 to 0.2 to 0.3 to 1 to 2 to 3 to 4. It gradually, continuously increases its speed. And if you had a very good camera, a very good high-speed camera, and took pictures of the speedometer, right, as you accelerated, you would see every single intermediate speed. What we're saying is that electrons don't act that way. The electron acts like a quantum car, where you would go from 0 to 5 kilometers per hour, to 9 kilometers per hour, to 21 kilometers per hour without ever going through the intermediate speeds. Like I said, it's weird. It's not the world we live in. We live in a world of continuous energies and speeds, but the electron does not. The electron lives in discrete, allowed and unallowed. Allowed energy levels 1, 2, and 3. At any other energy levels are not allowed. Okay. We're about to wrap this up. All right. And, whoops, sorry about that. Here, let me see if I can move my picture. Okay. All right. So Bohr did this work in the context of something called the hydrogen line emission spectrum. And in the hydrogen line emission spectrum, we do a very simple experiment. We take hydrogen gas and we put it in a glass tube and we pass a powerful electric current through that gas. And what happens is that, and these are different gases. I think one is neon. I think that's neon. There's krypton, there's argon, there's helium. These are the noble gases. Okay, so basically we're just saying that you put a gaseous element in a glass tube and you have 2 terminals and you create a powerful electric potential, and what happens is that eventually the gas glows a certain color or colors. So what we're saying is that when you do this experiment with hydrogen gas and you capture the colors, or you break down the colors and the wavelengths, once the gas is glowing, right, you see 4 lines. This is the hydrogen line emission spectrum. You see 4 colors and 4 lines only. You don't see anything in between these or these or these, right? Discrete, allowed states. And for hydrogen, this line is at 410, this is 434, this is 486, and this is 656 nanometers. And remember that we're going towards increasing wavelength from left to right. That's from from violet to red, right? And of course, energy is going the other way. This is high energy, this is low energy, right? Frequency is also going the other way. This is high frequency, this is low frequency, and wavelength is opposite to both energy and frequency. All right? So keep this in mind. What's the interpretation of this? The interpretation of this is as follows. Now, these are chemical reaction equations, and you're going to be seeing a lot of chemical reaction equations in our study of chemistry. All right? But here's what's going on. You have hydrogen gas in a glass tube, H2 molecules, right? Not hydrogen atoms. Hydrogen exists as diatomic molecule H2, just like oxygen is O2 and nitrogen is N2, okay? And you excite this hydrogen gas with an electric current. And that energy breaks the bond between the two hydrogen atoms, breaks that chemical covalent bond, and you split the hydrogen molecule and you get two hydrogen atoms in the gas phase. Those hydrogen atoms are further energized, right, to give what are called excited states. We go from the ground state to the excited state. That's what the star means. The excited state of an atom is when its electron or electrons have been promoted to a higher Bohr energy level. And notice that we can get promoted to 410 nanometers or 434 or 486 or 656. And that's it for hydrogen. There are only 4 possible states within the visible spectrum. There are other states in the ultraviolet and infrared spectrum, but we're just talking about the visible spectrum for now. This is called the Bohr series. And however, once those atoms are excited, they're unstable, and they want to relax back to. So this is the ground state and the excited state. They want to relax back down to the ground state. The ground state is the lowest energy state, and just like, suppose you had a big boulder and you had a ramp and you push the boulder up the ramp and you're pushing and pushing and pushing, right? You're raising the potential energy of the boulder because it's getting higher and higher on the ramp. And it takes a lot of force and energy to do that. Then you let go. What happens to the boulder? It rolls back down to the ground. That's what's happening here. These excited hydrogen atoms are relaxing back to their ground state, and when they do that, they give up energy in the form of light. And that's why we see these lines, right? So the excited state at 410 nanometers relaxes back to the ground state, giving up 410 nanometers, right? Oh, I'm sorry, there's an error here. I'm sorry. This is not all 410. This should be 434, 486, and 656. Very sorry about that. I'll correct that. But that's what's going on here, right? And it's all consistent with the Bohr model. Okay, it's all consistent with the Bohr model, right? The Bohr model is saying that, okay, if you start with hydrogen in the ground state, which is energy level 1, you can excite that electron here or towards another higher discrete energy level, but nothing in between. And once the electron is excited at that energy level, say 3, this is 1, this is 2, this is 3, it'll relax back down to 1, or it'll relax back down to 2. And when it does that, depending on the energy difference, it's going to release a certain quanta of light energy at the specific wavelengths corresponding to the energy difference between these energy states. Okay? One last word on this, and that would be it for now. One last word on this, and that is this. The Bohr model was a tremendous advance, revolutionary, because again, this is the first time that a scientist of tremendous stature, postulated that electrons and atoms, atomic systems, are just different. They cannot be described by classical Newtonian mechanics, which worked for 350 years, Sir Isaac Newton, and they still work today. When SpaceX, right, launches a rocket, guess what sort of science they're following? They're following Newton's laws. They're not bothering with any of this, because those aren't atomic systems. Those are macro systems, the world we live in. Okay? It's only for atomic systems that we have this idea of quantized energy states, discrete energy levels, allowed and unallowed or disallowed, right? However, Bohr had that right, but what he had really wrong was he still had these red dots on these circles. He still felt that electrons were orbiting the nucleus at these discrete energy levels. And of course, we know that they don't. They don't orbit the nucleus. There's a probability of finding them in these different energy states at a probable distance from the nucleus. But we never know exactly where they are because of this, because of the Heisenberg uncertainty principle. And Bohr was not aware of the uncertainty principle at the time he developed his model. Okay. So anyway, that is I think all for now. I will say a few things before I wrap up. This is a much longer lesson than I would normally give online. Right? We've gone 30 minutes now, and I try to keep my flipped lessons, my online lessons, to 10 to 12 minutes at most, and there's always questions for students to work on, so that's something you also don't see. But I wanted to do this to at least give you a good introduction to me and my way of teaching and presenting material, and the enthusiasm I have for doing this, which is, I think you can tell, very genuine. All right, so I hope you enjoyed that, and I hope to hear from some of you who are struggling in chemistry or organic chemistry at whatever level, middle school, high school, college, university, even postgraduate level. I've helped hundreds of students improve their understanding and their test scores in chemistry, and I enjoy doing it very much. All right, so anyway, take care. Hope to hear. That's all for now.